We've seen that position, acceleration, and velocity can be applied in a rotational framework. And what is really interesting about rotational motion is then we can start applying everything else we've done uh, in linear motion to rotational motion. So we can talk about the kinematic equations. We can talk about Newton's second law. We can talk about energy and work and momentum. And so we'll start that here by talking about rotational kinematic equations. Here is just an easy summary of those kinematic equations. And we won't go through deriving these. The derivations are not terribly hard. But what you would discover is that if you have a constant angular acceleration, just like if you have a constant linear acceleration when we talked about the kinematic equations, then all of these equations are true. Okay, the terms match up exactly. Okay, so where we had velocity in the earlier equations, now we have angular velocity. Where we had position, we now have angular position. And where we had acceleration A, we now have angular acceleration alpha. So as long as we know how to do our kinematic equations linearly, it's not too big of a jump to be able to do some of them in angular terms. So let's do a quick problem. Oh, and remember, like I said, remember they're valid only when angular acceleration is constant, which is the only kind of problems we're going to have here in this class. All right, so here's our first problem. A fisherman hooks a fish that swims away from his boat. The reel is initially at rest, but it is accelerated at an angular acceleration of 110 radians per second squared. I got my units wrong there. The line unwinds at a radius of 4.5 centimeters from the center of rotation. So we see that in our image over here. How many revolutions does the reel make in 2 seconds? So this is just like a linear accelerate or kinematics problem, right? We know where we start. We know how fast we're accelerating. And we know how long we're accelerating. And essentially it's asking us, how far have we gone? Okay, how many revolutions has our fishing reel made? So we want to lay out our variables, and they look very similar to our kinematics variables. We want to know theta f, that is the final position. That's just like xf. So we'll put a question mark there. We'll call theta naught 0, so our initial position is 0. What is our velocity? Well, we start at rest, so our angular velocity initially is 0. We don't know what our final angular velocity is. And we know our angular acceleration. Again, I missed my units up here. And we know our time is 2 seconds. So real quick, we could say, oh, okay, I'm accelerating at 110 radians per second squared for 2 seconds. What does that mean my final velocity is going to be? Well, after 1 second, it's going to be 110 radians per second. After 2 seconds, it's going to be 220 radians per second. But we'll do a more formal way of finding out our answer here too. So just like in our kinematics, we don't really need this. So we're going to try and find an equation that gives us theta f, the unknown that we want, but doesn't include omega f, the unknown that we're not interested in. So we look at our kinematic equations and we decide on this one, right? It doesn't have omega f, but it's got theta f, which is what we want. And we can plug in our values here. initial position is 0, our initial velocity is 0, so this term zeroes out. And we end up with half 110 radians per second squared. I got my units right, woohoo! Times 2 seconds squared. And we find that our answer is 4 times a half times 110, which is 220 radians. So this is a distance, and that can trick people up here. That radians is a measurement of position. So it's just like putting meters in a linear problem. It just tells us how many times our rotation has gone around, 220 radians. Now, the question asked us for revolutions per second. And so we have to think about how many revolutions are equal to a radian. A radian, it takes 2 pi radians to get all the way around a circle, right? So that's going to be our conversion, is 2 pi radians is equal to 1 revolution. So we're in radians, so we multiply by unity. We put our radians in the bottom so that we cancel out our radians here. And we end up with 35 revolutions. So our fishing reel has turned around 35 times in those 2 seconds.